Bonding intermolecular forces. So what is it? So it's basically what happens when two elements combine and form a compound. There are two different variations, and we'll talk about it. And intermolecular force is basically the force between these compounds, the interactions between them, and we'll go into that a little bit more detail in a second as well. So let's get started. Let's first talk about the three different types of bonding. So first off, you have ionic bonding, which is made of a metal and a nonmetal. So what happens is that the metal and the nonmetal become ions, so they gain and lose electrons. Metal loses, nonmetal gains, and as a result of it, it produces these ions. And you can see in the diagram, these ions are now interspersed amongst themselves. So usually when people think ionic compounds, they just think of Na plus and Cl minus. That's not really what happens. It produces what's called a lattice structure. And that's what these two images show you, is that you have these cations interspersed in between all these anions. And it's basically set up, if you think through dimensionally, right now you can only see this sodium surrounded by 4 different chlorides. But in reality, it's 6. There's one behind it, there's one in front of it. This gives you a little better image of it, this three-dimensional rendering of it. But the gist of it is that it's not just a 1-to-1 ratio. I want to make that clear. It's going to be a whole bunch of them producing this lattice-like structure. So when you're trying to break these bonds, what you're trying to do is break these interactions between the positive and negative ions. We'll talk about ionic compounds a little bit more later, but for now, the only thing you really need to know, they're oppositely charged ions, and they produce a lattice structure, as you see in this diagram. That's in comparison to a covalent bond, which is going to be the bulk of this discussion. It's a nonmetal and nonmetal, and whereas with this, you could see the way it's designed, the positive and negative ions is what keeps the compound together. It's what keeps the structure the way it is. Whereas with this, with the covalent compound, it's not opposite charge that keeps it together. It's sharing of electrons. So each element technically donates an electron and creates this bond. And that's what allows the structure to exist. In terms of strength, ionic bonding is a lot stronger than covalent bonding. And then our third variation is metallic. And you can see the metallic is a little different. It's the way it's designed is that each metal has a nucleus that's attracted to electrons of another metal. And that in turn is what creates this structure together. So it's not opposite charges like it is for ionic compounds, not really sharing in a technical sense, though it is to some degree. It basically is designed so that two metals are interacting with each other based on a nucleus of one attracting the electrons of the other. The fascinating thing about this for metallic bonding, which we're not going to spend much time with, is the fact that these electrons are not obligated to stay in one place. Like this electron is free to move all the way over here to another metal. They were referred to as delocalized. And delocalized is a fancy way of saying they can't stay, or they don't need to stay in one place. They're free to move. And that's the reason the metals are such conductors of electricity, because the electrons are free to move wherever they want to, and electricity is nothing more than the movement of electrons. So metals are very good conductors of electricity because the electrons, once they go inside of them, they're able to move wherever they want to. So they're very good at conducting. They're also good at conducting heat as well for the same reason. Because the electrons are not able to stay in one place or don't have to stay in one place and they're moving all over the place, they carry energy with them. Most people think that metals heat up so that in a way where the two that are in contact with each other are transferring heat between them. That is true. But in addition to that, the electrons also transfer energy. So this electron here can transfer energy to this metal atom over here, and that's what allows it to heat up faster. All right, energy is involved in ionic compounds, so we'll talk about that first. Breaking ionic compound is always endothermic, which means you also put energy in. You can see here we have two compounds. These are both molecular, but the concept is still the same, is that you're putting energy into them to break the bonds, and whether it's ionic or covalent or even metallic, you're doing the same sequence of things. Whenever you break a bond, you put energy in. It's endothermic. Forming a compound is always exothermic. So in this situation, the forming of these two compounds, or any compounds, it doesn't matter what kind of compound we're referring to, ionic or covalent, they're always going to produce energy. And that's the part that really throws people off for a loop. That breaking bonds requires energy. That's kind of obvious. But the part where if you form a bond, you release energy, that throws people off for a loop a little bit. But that is actually an exothermic reaction. Energy for breaking and forming ionic compounds is called the lattice energy. We'll go into more detail about that in a second. So lattice energy is impacted by charge and size of the ions, with charge being the bigger factor. This is called Coulombs Law. Coulomb basically said that opposite charges or two bodies interact with each other, such that the force of attraction, which is we'll call F, is proportional to the charge of the first body times the charge of the second body divided by your radius squared. Now, these Q1 and Q2s, if you think about, like, let's say, solar system, that could be the gravity of the two objects. This basically applies to any two objects, as long as they have some sort of attraction between them. So what this is basically telling you is that when you multiply the charge of the two objects, and when we think charges, you don't think positive, let's say this is Q1 and Q2, that's what we're talking about this one. You're not saying positive 1 and positive 2, you multiply those together, positive 1 and negative 1. You're not multiplying those two together, because Li is a positive 1, fluoride is a negative 1. What we're really saying is 1 times 1 divided by radius squared. And the radius is the distance from one atom's nucleus and the other atom's nucleus. Now, lithium fluoride is a very small atom. They're both in period 2, right? So they only have 2 shells each. So it's a fairly small atom. So the radius will also be small. What this tells you, based on the way this equation is set up, is the bigger the distance between, larger this is, equals to smaller force of attraction, which in simple terms means that the bigger the atoms involved, the less attraction between them, because the radius, the distance between the two of them, is going to be fairly large. That's the gist of this. It also tells you that the bigger the charge, the greater the force of attraction. So when you're looking at this, look at 1,030, pretty large number, right? Then you go down. Why is it decreasing? If you notice, these are all positive 1 and negative 1s, right? As you go on down, these are all positive and negative 1s. So why the heck is the force of attraction decreasing? Well, what's changing? The charge isn't, right? These are all positive and negative 1s. What's changing is the radius, right? Because if you notice, chlorine is bigger than fluorine. It's 1 shell underneath, has 3 shells versus fluorine's 2. Iodine's bigger, sodium's bigger, and so on and so forth. See, sodium is also bigger than lithium. So these are all things you come into play. So the first thing you want to look for when you're trying to figure out what has the greatest force of attraction is the two atoms' charge. The bigger the charge, the greater force of attraction. That's the number one variable. That's the biggest impact. Secondary, if the charges are the same, you look at the difference in size. And the bigger it is, the less force of attraction. Case in point, look at magnesium chloride. You see how this is 1,030? This is 2326. Why is it almost double? More than double, actually. Well, this is a positive 2, this is a negative 1. That positive 2 makes the big difference. And you could look at down here, scandium nitride, that's positive 3, that's negative 3. Look at the difference between these two. Massive difference. What's the explanation for it? Charge. So the first thing you look for force of attraction is the charge, and the second thing you're going to look for is the difference in size. The atoms, when the charge are identical, like here, you see how all the charges are identical, plus 2, negative 2. So what's going to be the biggest one? The smallest. Magnesium is smaller than calcium, which is smaller than strontium, and look at what force of attraction is showing you. And you'll probably ask yourself, well, why do I care about this? This is what tells you which ionic compound is a higher melting point. The greater the force of attraction, the higher the melting point. And that's a big deal. It's also going to have the biggest lattice energy, which is a fancy way of saying the energy you need to break the compound. So those are all things you have to consider. You could see Coulombs Law in this diagram a little bit better. So there's the force of attraction between the nucleus of this and the electrons in the other, nucleus of this and the electrons of the other. You remember, charge is the biggest variable, radius is secondary. So there's your formula. F is electrical force between two atoms. Q1 and Q2 are the magnitude of the charge. No magnitude. It didn't say the sign of. So remember, you don't plug in positives or negatives, just a numeric value when you compute it. You don't really have to compute it. You just have to figure out that, oh, this is a bigger charge. It's going to have greater force of attraction. So that's what this is pointing out, is that the sign of the charge isn't important, just a number, which means -4 is bigger than +2. It's going to have a bigger impact. So don't think in terms of number line. That's going to confuse you in the concept. All right, so let's move on to Lewis dot diagrams. How do you draw Lewis dot diagrams? First thing you need to do is add the valence electrons for all elements in the compound. So what this means, let's say we're doing CH4, for example. So if you look in the periodic table for CH4, carbon is in group 4A, so that's 4 valence electrons. Hydrogen is group 1A, so that has 1 valence electron. Your number of valence electrons is based on the group number. So group 1A has 1, 2A has 2, 3A has 3. We're going to skip all the transition metals. Transition metals are not applicable to this because they're metals. We're only concerned with non-metals. So group 3A has 3, 4A, 5, 6, 7, 8, all the way into noble gas, which have 8 valence electrons. So carbon has 4, hydrogen has 1, but there are 4 hydrogens. So what we do is we're going to multiply the valence electrons by the subscript to give us a total of 4 valence electrons for that. That's 8 total. That's what I mean by add your valence electrons. If you want another example, let's say we're doing CO2. So that's 4 again. Oxygen's group 6A. 6 times 2 is 12. So that's 16 electrons. So that's what I mean by you add your valence electrons together. So we're going to figure out the total number of valence. That's the first thing you always have to do. If you don't do this, the whole system is going to be screwed up. Place the lowest quantity element in the middle and connect to the rest of the elements. It's a shortcut that works. Really, it's the most electronegative element. If carbon's involved, carbon is your middle, without a question. And I'll give you a complicated one just to give you a comparison between these 2 variations. Let's say we have C2H4. So there's 2 carbons and 4 hydrogens here. So that's a total of 4 times 2, which is 8, plus 4 times 1, which is 4. So that's 12 electrons. So let's draw the Lewis structure for all these and see how it plays out. So the one you have less of is the middle, and you connect the outsides to it. So here's one hydrogen, here's another hydrogen, here's another, here's another. Here, same thing. Here's your carbon. Connect. All you do is just connecting it. Now I do want to point out at this point that for here, use the total of 2, 4, 6, 8 electrons. Each line is 2 dots. So this is the same thing as saying this. So why do you want to do a line versus dot? It's cleaner, it's easier to see, but if you love dots, go with it, I guess. So when I'm doing this, I'm doing a total of 4 electrons, right? That's important. You're going to see how this plays out in a second. For C2H4, I'm going to do it as dots just so you can see the comparison. The problem with this is that we have 2 carbons. So when you have multiple carbons, each one of them is a middle, which is a weird way of saying that you don't have a single middle anymore. So we're going to do this. So whereas this had a single middle, this had a single middle, and everything else that just involves usually a single thing like, well, these are all carbons, but if they involve elements where you only have one middle, which is basically any compound that's not carbon-based is only going to have one middle. So if I give you, let's give you an example of this so you can see what I'm talking about. If I say BF3, there's only one middle here. So it looks like this. What you don't do is this. We don't do BF connected to another F. We don't do that. That indicates multiple middles. Each time, excuse me, you connect the central atom to something like you did here and like you did here, you're indicating that it's another middle. So there's multiple middles according to this, but it's not possible. So just ignore that. So this, when you have carbon compounds like this, when you have multiple carbons, they're mirror images of each other, which is saying basically that you take the other elements and you equally distribute them around those 2 middles. So instead of putting 4 or 3 hydrogens off of this carbon and 1 on this one, you're going to put 2 and 2. That's the way it always plays out. So I'm just going to put 1 here. Does it really matter which of the 3 locations? Because there's only 3 options, right? Either up, left, or down. No, you can put wherever you like. So that's what I mean by connecting. Now, how many electrons did I use? For this one, I used 8. For this one, I used 4. And for this one, I used 2, 4, 6, 8, 10. Why is that important? Look at the total count of a number of electrons you have. You only have 12 to play with. You only have 16. You have 8. So for this one, I've used up all my electrons. I can't put any more electrons down. For this one, I have 12 more available. For this one, I have 2 more available, and you'll see how that plays out in a second. Use electrons left to give this elements on the outside 8 and put any left over in the middle. So for this one, we don't have any left over. So this is your Lewis structure. You're done. The objective for any Lewis structure is to make sure everything that wants 8 has 8 valence electrons. Carbon wants 8 every time. Hydrogen only wants 2. So as soon as you connect hydrogen, you're done with hydrogen. Don't ever do this with hydrogen, or this kind of silly thing. Don't ever do that with hydrogen. These are bad. Only thing you're allowed, connect hydrogen, call it a day. So CH4 is done. What about CO2? Well, let's start out where we were. Now, outside, right? Everything on the outside must have 8, so we're going to go with that. But we have 4. Now we're going to connect the rest, right? So we have a total of 12 left, right? 16 minus 4 gives us a total of 12. So watch how I do. 2, 4, 6, 8, 10, 12. So I connected the middle to the outside, and then I made sure everything on the outside has 8. The only exception for the 8 for the outside elements is hydrogen once again. Hydrogen only wants to be connected. There is no outside for hydrogen. So then we go to the next one, which is your C2H4. Once again, notice that they all have 8. The carbons are irrelevant at this point. I'm sorry. The hydrogens are only connected. You don't need to give it 8. So we're going to just give it, I'm going to keep it as is. Okay, then we're going to go on. If central atom doesn't have 8 electrons, then double and pair, make 2 pairs, or triple bonds are involved. So for the first one, we're already done. We don't need to do anything else. This is fast Lewis structure, call it a day, move on with your life. For this one, you see how you only have 2, 4 electrons? See how the middle one does not have 8, right? There's only 2, 4, but it wants 8. Everything wants 8, especially the central atom. There's an exception for that, but we'll talk about that in a minute. So what do I do? In that situation, you erase and move. What does that mean? You take an electron from the outside and you move it over here. Now, when you do that, this thing still has 8 electrons, right? Because all you did was just share more. You still count this moved electron as part of this oxygen's 8. But that still only gives carbon 6 electrons, 2, 4, 6. So what I do now? Erase and move again. And you put it over there, and when you do, what happens is that now this, once again, has 8, because the oxygen still has 8. But now the carbon has 4 plus 4, that's 8. So this is what it looks like. And on your paper, you just be erasing and moving. I'm just showing you how it looks. So this is the way it would look here. So you notice 4, 6, 8, 4, 8, 2, 4, 8. Everything has 8 that wants 8. You're done with the Lewis structure. These are called double bonds. The only time you do double and triple bonds is you're short on electrons. So after you put all your electrons on like I just did, and you look at the middle and you're like, oh, it doesn't have 8. All you need to do, erase from the outside, share in between. You could do that up to 6 electrons, no more. 6 is your cap. So take a look at this one. What do I have? I have 2, 4, 6 for this carbon. I have 2, 4, 6 for this carbon. That's no good. We want 8. So how do I do this one? Well, the only difference with this one is that we have a total of 12 electrons originally, right? We used 10, 2, 4, 6, 8, 10. We have 2 left. So what you're supposed to do really is put those extra 2 off of the middle. Now, when you do that, you should have recognized, wait a second, if I put 2 here, that gives this carbon 8, that's happy. But this carbon's sad, it only has 6. So how do you fix that? Same thing we did a second ago. You erase and move between them. So now this one becomes like this. And now you're sharing 4 electrons between them. And that makes it a much more stable structure. So this is a double bond, and you see how I figured it out is based on the fact that I put all my electrons down, realized I was short, erased and moved. That's what you're supposed to do. That's the easy way to do these Lewis structures. Resonance, it refers to compounds with double bonds that can be placed in more than one location. So when you're doing your Lewis structure, sometimes you have a situation where you could choose. I could put the double bond here, I could put it here. When you have that choice, you have resonance. Exceptions to the octet rule, boron only wants 6. So once you get boron, 6 electrons is done. So like for that BF3 earlier, this is the way BF3's Lewis structure would look. Notice this only has 6. Do not give boron more than 6. Do not erase and move. Do not do double or triple bonds. You'll be wrong. Boron only wants 6. Elements in period 3 and beyond can have more than an octet. What does that mean? Well, period 3 and beyond has a D block, right? Because D begins in the third shell. So because of that, elements can do something like this, which is pretty crazy. Notice we have 4 electrons. We have 8 right now, right? This is what they can do. They can do this crazy stuff. They don't have to, meaning that don't force this. If you don't have 6 chlorines, don't just add them for fun. Like if I give you SCl4, don't draw this. But if I give you SCl6, this is the way you draw it. You don't connect the chlorines together. The only time you can have multiple middles really is when there's carbon involved. For the most part, there's a couple of situations where oxygen, but let's just roll with carbon's the only one that's going to have it for now. And we'll talk about the variations later. So for this one, you have 6 around it. So what does that do? It gives you 2, 4, 6, 8, 10, 12. 12 electrons around sulfur. Yes, sulfur can do that. Why? Because period 3 and beyond. Can nitrogen do this? No. Nitrogen in period 2. Nitrogen cannot do this. But sulfur and elements from period 3 and beyond can. They don't have to, but they can. Just remember, if you have extra electrons also, you stick it off the middle, and we'll talk about some examples of that a little later. And hydrogen only wants 2. Once you give hydrogen 2, call it a day, move on with your life. Don't complicate situations. So let's show some more examples. So we already did CO2, so we're not going to repeat that one, obviously. Let's do SO3. So SO3, group 6A, so it's got 6 valence electrons. Oxygen is also 6A, and there's 3 of them, so 6 times 3 is 18, so that gives us 24 electrons. Carbon, 4 plus 6, 10 electrons. Nitrogen, 5 plus 5, because there's 2 of them, right? Group 5A, 10 electrons also. I have 5, that's 7, plus 5 times 7, because 4 is group 7A, 35, equals 42. So let's start with sulfur trioxide. So sulfur is your middle. Connect to the outside. 1, 2, 3 connections. That took up a total of 6 electrons. We have 18 left. So we're going to fill it outside, inside, right? 2, 4, 6, 8, 10, 12, 14, 16, 18. And then finally, we look at the middle. Does the middle have 8? Well, the middle has 2, 4, 6. So no, it doesn't have 8. So what do? Erase and move. Does it have 8 now? Yes, it does. So this is the proper Lewis structure for it. But you notice that you had a choice where the double bond came from. You could have done here, here, here. This is called a resonance structure. So whenever that happens, you need to draw all variations, unfortunately. Here's one variation. And you have this double arrow to represent it. Here's the other variation. You notice all I did was move the location of the double bond from left to right to top. So that's a resonance structure. So yes, you have to draw all variations whenever it's a resonance structure, or whatever number of variations it is. Next one, carbon monoxide, CO, connect, right? What's the next thing we do? Outside in. So what's your outside element? Well, if carbon's inside, carbon is your middle. So we're going to work with oxygen first. So I use 2, 4, 6, 8. I have 2 left over. Where do I put it? Off the other element. You want to put all your electrons down. Don't anticipate double and triple bonds. Just put all your electrons down, take a look at it, and see if it's necessary. In this situation, carbon only has 4. So we need to move electrons. And as always, you move electrons to the one that has the most. So carbon only has 2 lone pairs, or 1 lone pair, I should say. Oxygen has 3. So we're going to move from oxygen. So we move it. Now, this once again, it still has 8, 4, 6, 8. But this one has 6, 4 plus 2. It's not adequate. So what do? Erase and move. Now 6 plus 2, 8, 6 plus 2, 8. So this is a triple bond. Different than the double bonds we saw a second ago. And there's your Lewis structure. So this and this will be removed. Nitrogen, the molecule. 10 again. Connect. Here, they both could be middle, so it's going to work on the right and go to left. So 2, 4, 6, 8, 10. There's our electrons placed down. It's the first thing you want to do. Once again, do not anticipate double and triple bonds. Then erase and move. That's 4, 6, not happy. Erase and move. 6, 8, 6, 8. We're good. So it just looks just like carbon monoxide. And then the next one, a little tougher, 42. Put I in the middle. So we have 5 Fs. Now remember, you can't have multiple middles. So this means that that fifth fluorine is going to have to be off the middle. So does it matter which corner? No. As long as you put on one of these locations, you're fine. So I have 42 electrons. So I use 2, 4, 6, 8, 10 electrons. So I have 32 left. So watch me count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. I have 2 left, right? So what do? Do I create a double bond? No. Only do double and triple bonds when you're short on electrons. When you have leftovers, just stick it off the middle. Doesn't matter where? No. You could put it as a line, you could put it as 2 dots, whatever makes you happy. But that's what you do when you have extra. Just stick it off the middle. All right, polarity and covalent bonding. Electronegativity, the attraction of an atom has 2 electrons. So we talked about this a long time ago with periodic trends. You can see the trend increases as you go to the right. You'll see the noble gases are completely missing from this chart, and the reason they're all 0. Noble gas has 0 electronegativity. So polarity is determined by whether you have an equal or unequal attraction of electrons. So the easiest way to deal with this for polarity, if the elements are 2 different elements, assume it's polar. Fastest way to do it. Only exception if it's CNH. If it's CNH, that's 2 different elements, that's nonpolar. So that means that if I do CO, polar. If I do CF, polar. If I do PCl, polar. All these are polar. Just make your life easier and look at it that way. The only time it's nonpolar and it's 2 different elements is this. So these are all polar bonds. Unless you want to sit there and calculate the numbers, which I don't think you want to. Shortcut is, if it's 2 different elements, it's polar. If it's CNH, it's nonpolar. What if it's a CN element bond to itself? Obviously polar. What else are you going to do with that kind of situation, right? All right, let's see how this applies. So polar covalent bonds found in molecules where the electrons are more attracted to one element than the other. So I give you the shortcut. 2 different elements, it's unequal sharing. That's that's a polar covalent bond. So anytime 2 different elements are bonded, CNH polarity exists. Anytime there's a lone pair off the central atom, the molecule is polar. So there's 2 types of polarity to be aware of. The polarity of the bond, the polarity of the molecule. So you're probably looking going, what the heck does that even mean? So I'll give you an example. Let's say we do CF4. So here's my Lewis structure. So you see how this is CF? That's a polar bond. The bond between these 2 is polar. The bond between these 2 is polar. The bond between these 2 is polar. The bond between these 2 are polar. Wonderful. We'll refer to this as a symmetrical structure, which means that the F's are opposite each other all the way across. And that means that they cancel each other. So the polarity of this, like this molecule pulls this way, polarity-wise. This molecule pulls this way, polarity-wise. They cancel each other's effect out. because it's symmetrical and because the same element on opposite sides, this molecule is nonpolar. The bond is polar, but the molecule is nonpolar. And that's because, once again, the polarity cancel out. It's like, identical strength people pulling, someone in the middle. They're not going to make them budge because they have equal strength. That's what's going on here. So there is no unequal sharing because they all cancel each other's effect out. Now, that's different than if you have this. If you have this, it's a polar bond, right? Two different elements. And here, the polarity, the electrons are being pulled toward the oxygen, which is more electronegative. And there's nothing to cancel that out, right? So this molecule is polar. The bond is polar. There's nothing to counteract that. There's no only the opposite side to do it. Now, as far as what it's referring to here with the lone pair, this is what this means. So if you have a lone pair up the middle, you actually have a polar molecule. So anytime. So let's say NH3, for example. Here's a lone pair. So here, equal pulling, and it should actually be facing the nitrogen. The arrow points to whatever is more electronegative, in case you didn't catch that. Nitrogen is more electronegative than hydrogen. And then you have going this way. So here's what's going on with this. This lone pair makes the molecule asymmetrical. So instead of being able to cancel each other's effect out, they can't. They're all being twisted. Like these H's are not opposite each other. Because of this lone pair, they're doing this kind of thing. You see how this H is going this way, this H is going this way. They can't cancel each other out. Even if there was another H, it wouldn't matter. Because of that, because it's asymmetrical now, this molecule is polar rather than nonpolar. That's what. And anytime you have a lone pair up the middle, polar. Move on with your life. Don't overanalyze. Don't think. It is always going to be polar. The other thing I want to point out is if the molecule is resonance, it's also nonpolar. So like SO3, we did that earlier, right? This is a nonpolar molecule. Why? Because resonance structures are always nonpolar, unless there's a lone pair up the middle. So if I do this instead, this is another, this is another version of it, of SO2. This has two different versions, right? Because this has a lone pair up the middle, this molecule will be considered polar rather than nonpolar. So anytime you see a lone pair up the middle, polar. Anytime you just see resonance with no lone pair, nonpolar. Anytime you see symmetrical, nonpolar. And anytime there's just two different atoms, polar. A lot to remember, I know. So we've been doing dipoles this whole time, that little arrow thing. You see how the arrows point to whatever's more electronegative. This is a positive dipole, it's a negative dipole. This is telling you this is less electronegative, this is more electronegative. That's all this positive and negative sign means. Arrow also is another way of representing. These are both ways representing polarity. So if dipole moment is 0, due to symmetry, the molecule is nonpolar. So here's CO2. See how the arrow is pointing this way, arrow is pointing this way, positive, negative, negative. This is symmetrical, so the molecule is nonpolar. So drawing dipole, draw the arrow between the two atoms such that it is pointing to a more electronegative element. Here are some different examples of it. CH2O, you see CH4, CO2. Placing dipoles, you put the negative dipole, whatever's more electronegative. So negative, negative. This is, as a result, has to be positive. They don't have to equal out. It's not like, you need to have two positive and two negative. It's not that kind of thing. Whatever is more electronegative becomes negative dipole. Whatever has less electronegativity becomes positive dipole. That's all you got to do. Don't overthink this. These are all different examples of it. All right, nonpolar molecules. Here's Cl4. Remember, it's symmetrical. How do I know that? Because there is one carbon and 4 chlorines with no lone pair. The chlorines will all cancel each other's effect out. This is tetrahedral structure. We'll talk about what the shapes are in a little bit. But even though it doesn't look like it's symmetrical, it is. It's just in a three-dimensional realm. This is nonpolar. This is nonpolar. This is nonpolar. This is probably a tough one to look at. And you're like, wait a second. They can't all cancel out. No, the shortcut. So shortcut tip. When it's just C and H, it is always nonpolar. So if you see, you could have a huge molecule, but just CNH only, nonpolar. Move on with your life. If I put any other element in there, I could put an O, I could put a BR, or polar. It's that simple. So when you have a hydrocarbon, and it's just hydrocarbon H and C, nonpolar. Any other element, doesn't care what it is, where it is, it's going to be polar. Ultimate shortcut. All right, formal charge. This is the way you could tell which Lewis structure is the most desirable in a situation. You want to put a -1 charge on most electronegative element and 0 on the rest. So I'm going to show you how to do this. So the way the formal charge works, you can look at the group number the element's in. So for carbon, that's group 4A, right? So 4, minus the total number of electrons surrounding that element. Lone pairs count as 2. For bonded, you take half of that total. So there's 6 electrons here, right? 2, 4, 6. So half of that is 3. So watch how the number works. So it's going to be 4 minus 2 plus 3. That's 5. So this gives me a -1 charge. For CO, you have a total, this is group 6A, by the way, right? Oxygen is group 6A. 2 plus 3, which is 5, gives me a +1 structure. A -1 and a +1. So we're going to give you another more complicated example in a second just so you can see it. But formal charge is equal to the group of the element minus half of the bonded minus number of lone pairs. So let's take a look at a more complicated example. Let's look at SCN. So thiocyanate has a -1 charge. So we're going to deal with first drawing the Lewis structure. And this one's a little more complicated because there's a charge involved. So we're going to talk about how to deal with those. So sulfur has 6, right? Group 6A. Carbon has 4. Nitrogen has 5. So what do you do with the negative charges? When it's a negative charge, you add that many electrons. So -1, you add 1. -2, you add 2. -3, add 3, so on and so forth. If it's positive, you subtract that many electrons. So in this situation, it's -1, so we're going to add 1 to our total. So it's 10, 15, 16 electrons. I'm going to put C in the middle, because that's our most electronegative typically, right? Put N in one corner, put S in the other. And in this particular situation, you have 2, 4. I have a total of 12 more. So 2, 4, 6, 8, 10, 12. Now look at the middle. Middle doesn't have 8. So what do? Erase from whatever has more. Erase from whatever has more. Now you have 4, 8, and they're both, everything has 8 now, right? When you have an ion, you do also have to do this thing. You put it in brackets and the charge on the outside to make it clear to the person looking at it, this is actually an ion. So the other thing you have to do now is, if you look at this, this is one possible Lewis structure, but theoretically, we could also do this, no? Technically, this also has 8 for everything once 8, right? 6, 8, 6, 8 for the carbon, 2, 4, 6, 8 for nitrogen. Seems like both are valid, right? If we're doing it the method I'm showing you, you won't be doing this, right? Because they're a very specific system to avoid that kind of stuff. But let's take a look at the formal charge for you, just to understand formal charge a little bit better. So for sulfur, it's group 6A minus half of, this is 4 electrons, right? So half of that is 2, 4, 6. So 6 minus 6 is 0. For carbon, it's group 4A, half of 4 is 2, half of 4 is 2, 2 plus 2 is 4. Or you could look at it as 2, 4, 6, 8 divided by 2 is equal to 4, so that's 0. And in nitrogen, group 5A, you have 2, 4, half of 2, half of 4 is 2, so that's going to be 2, 4, 6, that's a -1. So nitrogen is the most electronegative element here, right? And it's got a -1 charge, what we want. So this is the correct Lewis structure. So the formal charge really comes in when you only have one choice. Like here, for CO, you really didn't have a choice. I mean, I could give you the formal charges, but if you look at it, oxygen is more electronegative than carbon. So it's like, wait a second, that kind of contradicts it. That's when you have choices. Here, you do not have a choice. There's only one possible way to draw the Lewis structure. For this one, there's 2 choices. So here you see it's a -1 for most electronegative. Everything else is 0, which is what we want. But what about this one? Let's take a look at it. So you have 6 minus 3 plus 2 is 5. So that gives us a positive 1. Already we're kind of in the wrong direction, right? Carbon, you have 4 minus 3 plus 1, 4. That's 0. Okay, that's fine. And here we have 5 minus 2, 4, 6, 7, negative 2. That's a big no-no. You don't want to get to negative 2 world. 0 and negative 1 is ideal case. So if we had to pick which one of these is the more logical structure, we pick the top one. Why? Because the most electronegative has a negative 1 and everything else is 0. That's what you prefer. Now you could have 2 negative 1s, you could have all zeros, that's all fine. What you don't want is this. This is a big no-no. You don't want negative 2, negative 3, those are all very bad. So that's how you figure out the formal charge. And the whole point of formal charge is to tell you which is the best Lewis structure when you have choices. You don't always have choices, obviously. All right, so draw the Lewis structures and determine the polarity and formal charge for these. All right, so start with NH3. You have 5 plus 3, that's 8. So connect, connect, connect. We have 2 left over. Drop it up there. Formal charge. Group 1A minus half of 2 is 1. So all these hydrogens are 0. I'm not going to do all of them. Nitrogen now. You have 5 minus 1, 2, 3, 2, 0. All right, and that's because of the fact that this counts as 2, lone pairs counts as 2, and then half of these 1, 2, 3, these 6 electrons will give you 3. So 3 plus 2 is 5, so you get 0. So there's your loop formal charge. SO4, you have 6 plus 24 plus 2, 26, 32 electrons. So S in the middle, O, 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 O. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. There's all my electrons. Beautiful. Everything has 8 that wants 8. Bracketed, negative 2. Now the formal charge. So this O is going to be 6 minus 2, 4, 6, 7, right? That's negative 1. So these are all going to be negative 1s on the O's. The sulfur is going to be 6 minus 1, 2, 3, 4. Positive 2. So when you look at this one, you're like, whoa, that looks really bad because you have 2, 4, 6, 8. How do you, that's not a number we want, right? We want zeros. Do you have any other choices for this one? No, you don't. You can't put O with an O. That's not going to work. There's only one central atom. So here, even though I figured out the formal charge, you don't have a choice. It's not that you could have another scenario. It's possible for this. You can't do double bonds and triple bonds because that's a definite no-no because you have more than enough electrons to give everything 8 without doing that. So that's the other thing I want to point out. You can't just get double and triple bond happy when it's not necessary. Here, it's definitely not necessary enough electrons. For SCN, you had no choice. You need to do that because you didn't have enough. 16 was not enough to get everything 8 to 1 at 8. All right, let's take a look at O3. O. That's a total of 18 electrons, by the way. So 2, 4, 6, 8, 10, 12, 14, 16. We have 2 left over. What do I do? Some of you guys will be like, oh, let's do a double bond because you know you have, no, but don't anticipate. Put all your electrons down. Look at it. Does it have everything have 8? O doesn't, right? You knew that before you even put it in there. That's 6, but all I need to do is just remove from here or remove from the other side, right? This is a resonance structure. Keep that in mind. By the way, just for fun, this is polar. This is non-polar because it's symmetrical, right? All the O's cancel out. Forgot to mention that because that was part of the question. For this one, it's resonance, so you should be like, oh, that's non-polar. Yeah, but lone pair after middle, polar automatically. So it's going to be asymmetrical. It's actually going to be a bent structure, but that's beside the point. So let's do this O first. So we have 6 minus 1, 2, 3, 4, positive 2. This O, we have 6 minus 2, 3, 5, 1. This one, you have a total of 6 minus 2, 4, 6, 0. So those are your formal charges. And then for the other resonance structure, it'll be the same, right? The same values. 3 different numbers, but for the same elements. So it's kind of weird because when you look at it, you're like, wait, positive 2, that's another. Yeah, but the issue is that there's three different possibilities here, so that's a moot point for this one. And SCN we already did, so we're not going to do that again. But that's how you figure out the formal charge and polarity. And this, by the way, remember, is polar. And SCN, in case you're wondering, that is also polar once you draw it. All right, molecular shapes. The shape of the molecule. This is a result of the atom trying to minimize electrons from repulsion, which is a fancy way of saying that atoms want to be as far away from each other as possible because they will repel each other. Because this has an electron cloud, this has an electron cloud. So to minimize repulsion, it takes a linear route. They're complete opposite directions of each other. For bent structure, what's going on is that there's two lone pairs here that you can't see, and those are pushing down on the structure. So this is the best shape it can take because it turns out the lone pairs repel more than bonded pairs. So these push those O's down, and that's what creates that shape. For trigonoplanar, this is the maximum or best distance between the molecules, which is about 120 degrees, in order to minimize repulsions. Same thing with this, trigonopyramidal. There's a lone pair here you can't see. T-shape, there's actually two lone pairs here you can't see, and that's what's creating the shape. So all these shapes are a result of molecules trying to minimize electron-electron repulsion. It's called Vesper Theory. So it determines the shape of the molecule. So Vesper says electron pairs should be placed as far as possible from each other, which is what determines their shape. So the shape is basically a product of trying to minimize those repulsions. Just keep that in mind. All right, we're going to figure out how to do these shapes based on what's called electron domains. Domains are just regions of electrons. So this, and you only look at the middle, by the way. Don't look at the outside. We don't care. Shape is always based on the middles. If you have multiple middles, then each middle will have each shape. All right, for this one, this is one region of electrons. This looks like it's two regions, right? Because it's a double bond. No, just one region of electrons. Whether it's a single bond, a double bond, a triple bond, or even a lone pair, it just has one domain. So there's 1, 2, 3 bonded domains, that's what we're going to call them, and one lone domain. So 3 bonded and 1 lone. 3 plus 1 would give us typically a trigonopyramidal structure, and we're going to go into how to figure that out. But that's what this means. It has a total of 4 domains, but it's 3 bond and 1 lone. And you want to make that distinction. So linear will be 2 domains total. Trigonoplanar 3. 4 will be tetrahedral. Trigonobipyramidal 5, and octahedral 6. As far as the angles and stuff you're seeing here, the only ones you really need to know the angles for is linear, you need to know is 180. You need to know that trigonoplanar is 120, and tetrahedral is 109.5. That's a big deal. This, don't worry about the angles, but know the shapes. Know that if you have 5 domains, trigonopyramidal, and if it's 6, you're going to have octahedral. You need to know that part. All right, some other shapes you need to be familiar with besides those. Trigonopyramidal is going to be 3 bonded and 1 lone pair. So you notice there's a total of 4 domains for this one. So you're like, oh, that's going to be tetrahedral because that's what 4 domains are. No, you need to make the distinction between lone pairs and bonded. So here you notice how there's 4 domains. All of them are bonded, so that's tetrahedral. Here it's 3 plus 1, so that's going to be trigonopyramidal. It's a subcategory. Notice the bond angle is different. Lone pairs, once again, cause a shrinkage of the angle between the atoms, and that's because the lone pairs push everything away more. So do you need to know it's 107.5? No. But what you do need to know is that each time you had a lone pair, the bond angle is going to shrink. So if your original was 109.5 and you have 1 lone pair, you just assume it's going to be less than 109.5. What if it's 2 lone pairs? It's going to be much less than 109.5. It's going to be somewhere between 105 and 109.5. It's about 2-degree difference per lone pair. That's like a general estimate, but you don't need to know the exact thing. You just want to know that each time you had a lone pair, your angle is going to be shorter than what you expect for if it was all bonded. Case in point, this is going to be 2 plus 2, right? That's 4 domains. That's basically a subcategory of tetrahedral. But you notice there's 2 lone pairs. So what are the 2 lone pairs doing? They're pushing everything down. It's creating a bent structure. Bent. So is this polar or non-polar? This is polar. What about this one? Polar. Lone pair, right? What is this? Non-polar. Why non-polar? They're all symmetrical. They're canceling out. This is obviously polar. We already mentioned that. All right, square planar. This is subcategory of square planar from octahedral. So octahedral has 6 domains, right? This is symmetrical, in case you didn't notice. So that's going to be nonpolar, in case you're wondering. Same element. I do want to point out, though, if you make this just randomly a BR, now it's polar. It's symmetrical still, right? But this BR can cancel the F. So please remember that. The only time the whole symmetry comes into play was the same elements on the outside. If they're not all the same, their symmetry may be symmetrical, but guess what? It's still going to be polar. For this one, square planar, you can see you have this. This is the only time, and I want to make this very clear, square planar is the only time that even though there's a lone pair, it's non-polar. And you ask yourself why? These 4 F's exist on one plane. The 2 lone pairs exist on a separate plane. Remember, it's 3-dimensional. So the lone pairs have no impact on the fluorine. So as a result, this molecule is considered nonpolar. It's the only time that there's lone pairs and it's nonpolar. So it's important to note that. All right, so trigonometry notice there's 5 domains total. This is also symmetrical. I know, looks crazy. How's 5 things symmetrical? They are. Remember, it's 3 dimensions. The subcategory for this is going to be T-shaped, and it's whenever you have 3 bonded and 2 lone pairs. And for this one, this is actually going to be polar. This was non-polar, by the way. This is the hardest one because you look at it like 5 non-polar. Yeah, it is. Seesaw, also a subcategory of trigonometric pyramidal. So you notice this is non-polar again. Here it says 1 lone pair. So when you have 2 lone pairs, you're T-shaped. When you have 1 lone pair, you're called seesaw. And you do need to know these subcategories. Here's again octahedral. Subcategory for it is square pyramidal, and that's when you have 4 plus 1 lone pair. So these subcategories are a result of having lone pairs. So when you see lone pairs, that's when the subcategories come in. This is polar. This is polar. Those other 2 are non-polar because they're the original structures. All right, so let's take care of this shaping polarity of each of the following. So CH3Cl, so HH. Hopefully you're at a point where you understand how I'm drawing this without having me go through all the details. This is symmetrical, first off, so this is tetrahedral. But the H and Cl can't cancel. Remember, so your polarities, your dipoles will look like this. And unfortunately, this does not cancel. The H and Cl can't cancel. This is actually polar. NO2 minus, I'm going to work this out a little bit more detail because it's a harder question. So 5 plus 12 plus 1 gives you 18. So put N in the middle. O, O. So that's a total of 18 electrons. So 2, 4, 6, 8, 10, 12, 14, 16. Remember, leftover, just take it off the middle. Does everything have 8? No. So it's a resonance structure because you could put a double bond here or here. Remember, charge in brackets because it's an ion. So what would this be? Polar. It is resonance, but it's got a lone pair off the middle. That makes it polar automatically. As far as shape is concerned, this is another subcategory we haven't talked about. When you have 2 bonded plus 1 lone pair, you actually have what's called a bent structure again. So this is actually bent. CS2, carbon, double bond S, double bond S. I shortcut it because I know what it looks like. Symmetrical, right? You can see that the dipoles will cancel out because it's symmetrical, same atoms on opposite sides. So this is going to be non-polar. As far as the shape is concerned, linear. So 180 for the bond angle, in case you're wondering. This is going to be 109.5 for the bond angle. I didn't ask, but that's what it is. This is a bent structure, so it's going to be less than 120 because this is a subcategory of trigonoplanar, which has 3 domains. So for trigonoplanar, the bond angle is 120. So because I have a lone pair instead of a bonded, it can be less than 120. Doesn't matter what the exact is. XEF4 is another telephone we're going to do. That's going to be a total of 36. Yes, xenon, the noble gas, you have to count the total number of valence electrons, which is usually 8, except for helium, obviously, right? So here's F, here's F. I'm going to draw it like this because it's what's going to look like. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. You have 4 more electrons, so here and here. This is square planar. Do you have to draw it with the shape in mind? Not really. As long as you can name it, you're fine. And for this one, it's going to be nonpolar. Remember, that's the one exception that we talked about earlier. All right, breaking bonds refers to the amount of energy you need to break your bonds. So these are covalent bonds. The bond speed, the energy you need to break. These are always positive. It's endothermic, guys. Endothermic means always a positive value for this. And if you notice, these are all positive numbers. They vary based on the element. The one thing I want you to see is that, see how the CC bond, single bond, right? Look at the double bond, almost double the energy. Look at the triple bond, about almost triple, well, 2.5 times the energy for the single. So if you're comparing elements or 2 elements bond together, as you share more electrons, the energy you need to break it increases because it's stronger. So basically telling you the triple bond is stronger than the double bond, is stronger than the single bond. That's as far as you need to go as far as, understanding how this is playing out. You're not going to memorize these numbers. You're just going to be able to use them. That's going to rely on your ability to draw Lewis structures. So calculate enthalpy from bond enthalpies. So your formula for this is bond enthalpies of bonds broken minus bond enthalpies of bonds formed. If you notice, this is kind of looks like the Prox minus reactants formula for enthalpy of formation questions. So the difference here, it's bonds broken, which is reactants minus products. Whereas if you're doing the other scenario, which is the enthalpy of formation, it's Prox minus reactants. So that's the thing you got to remember. It's reactants minus products. So how does this work out? You need to draw the Lewis structure for all these to be able to figure it out. So they'll give you this, which is your bond enthalpy values. You just have to be able to use them in the formula. So these are all the values. So there's how many CH bonds? It's a total of 4 of them. Why? Because when you draw CH4, there's 4 CH4s. Now, I do want to point out, if I put a 2 in front of this, if I put a 2 in front of this to make it 2 CH4, it will be 8 as your value, 8 times the CH bond, because there will be 2 sets of them, right? So keep that in mind. If there's a coefficient in front of any of these, you multiply that times the number of that bond you saw in your Lewis structure. So there's 4 ACH bonds. There's 1 CL-Cl, because it just looks like this, right? I'm not going to draw the lone pairs, but you get the idea. For this one, there's going to be 3 CHs. So 1, 2, 3. That's what it looks like. So how many CH bonds do you see? 3 of them. So that's why there's 3 here. There's 1 Cl bond, right there. That's what this comes from. And then the last thing, HCl, just looks like this. And there's the 1 bond for it. So now the way the math works, 4 times 413, that's for CH, plus 1 times 242, which is the Cl-Cl bond, minus products minus reactants, right? 3 times your CH bond, because there's a total of 3 of them, right? 1, 2, 3. And then plus 1 of the CCl bond, which is going to be right here, 328, because there's 1 here. And then finally, 1 of the 431. So as always, do the reactants alone, do the products alone like I did here, and then subtract. Please don't sit there and try to distribute this negative sign throughout. You're asking for a headache and a mistake. You don't want to do that to yourself. Just don't do that. So this is an exothermic reaction. So that means overall, this reaction is producing energy. And if you want to combine this with entropy concepts, there's 2 moles of gas on the reactant side. There's 2 moles of gas on the product side. So your entropy is close to 0. So what's the driving force of this reaction occurring, if you ask? It's going to be your enthalpy, right? So this is going back into thermal world. Because remember, change in G equals change in H minus T change in S. We said your S is basically negligible to 0, so that's non-existent. In order for this reaction to occur, your G has to be negative. So the driving force is whatever is going to make this G become negative, which in this case is your enthalpy, which we figured out was negative. What if this was a positive number? Then this reaction would be non-spontaneous. Simple as that. Because if this is positive, this would be positive as well, because remember, this is not impacting, and a positive G is a non-spontaneous reaction. So you can actually extrapolate this back in the thermal world and make some assumptions. All right, effective number of bonds, the other thing I want to go over. The greater effective number of bonds, the shorter the bond length. This is how you relate the bond length of one chemical to the other. So for example, SO3 is an effective number of bonds equal to 4 divided by 3 between S and O, so its bond length will be shorter than that for SO3. So let me draw both of these so you can see what the heck this is, because you're probably looking at this going, where the heck is he getting these numbers from? So here's SO3. Remember, it's a resonance structure. And SO2, excuse me, SO3 2 minus, which is the other one, will look like this. Brackets, negative 2 charge, and here's your lone pair. All right, so this is the way this works. You count the number of connections around the middle, ignoring the lone pairs. Lone pairs don't count. So we have 1, 2, 3, 4. Just count the number of lines, basically. That's all you got to do. So there's your 4, divided by the number of connections you saw. 1, 2, 3. 1.3. Right? Here, 1, 2, 3. You don't count the lone pair. Divided by number of connections. 1, 2, 3 again. You get 1. So which one has a shorter bond length? The one that gives you a bigger effective number of bonds, or bond order. They're the same thing. This is bigger than this. So this is going to have a shorter bond length. So once again, the bigger the value when you do this math, the shorter the bond length. All right, and close to the last thing, hybridization. I'm not going to bore you to death with hybridization, how it's developed and all. It basically tries to explain how some Lewis structures can even occur. So without complicating this too much, because the AP board doesn't even want to emphasize it to that level anymore. They just want you to understand what it is when you see it. So I'm just going to go to that level only. So this is all you got to do. Memorize. And this is how you do it. If it has 5 domains, it's DSP3. If it's 6 domains, D2SP3. So whether it's octahedral or square pyramidal, whether here is tetrahedral or bent or trigonopyramidal, they all have 4 domains, right? So here the number of lone pairs doesn't matter. You just count your total number of lone pairs. So however many lone pairs you have, that's what you're going to determine your hybridization. So if I have a linear structure, it's going to be SP. Why? Because if I have like CO2, right? That's a total of 1, 2 domains. 2 domains can be SP. You just have to memorize it like that. 3 domains can be SP2, SP3 is 4, D2 SP3 is 6, and DSP3 is going to be 5. That's all you got to do. Just go with that and you're good to go. So, sorry, you have to memorize some stuff. All right, so answer the following questions for I3. So let's try one. So I3, that's 21 plus 1, 22 electrons. So I in the middle, I, so that's 2, 4, 6, 8, 10, 12, 14, 16. You have a total of 6 more electrons, right? Because you did 2, 4, 6, 8, 10, 12, 14, 16. So you have 6 electrons. So I paused for a second because this is really weird, this particular structure. It's period 3 and beyond, so it can have more than 8 electrons around it. So that's not an issue. The mistake people usually make, they try to do double bonds with the i's. You never do double or triple bonds when you are not short. Only time you do double or triple bonds when you're short on electrons. You're not short here. So what we're going to do instead is put all 6 around the i. And look how I put them. Here, here, here. Does that have to look exactly like this? No. As long as you do 3 pairs around the i, you're good. All right, so this is the structure. And remember, brackets, charge, because it's an ion. What type of hybridization is around the central iodide? So what kind of hybridization is this? Remember, it's based on domains. That's all it is. 1, 2, 3, 4, 5. 5 domains is going to be DSP3. Because you have to memorize it by then. What type of hybridization is around the outside iodines? Well, that's going to be 1, 2, 3, 4. 4 is going to be sp3. That's for both of them. What is the geometry around the central iodine? This is really weird because you would think it's trigonopyramidal because it's got 5 domains, right? So here's the one exception you'll probably never see again in your life, but just be aware of it. If you have 2 bonded plus 3 lone pairs off the middle, you actually have a linear structure. Yeah, go figure. You'll probably never see that again, so don't worry about it. What's the geometry on the outside iodines? Well, you have a total of 1, 2, 3, 4 domains. 4 domains is what always? Tetrahedral. All right, so now let's get to the IMF stuff. So IMF, intermolecular force, are the force between molecules. So it's a force between these two. It's very weak compared to this, which is a covalent bond. Covalent bond is what bonds 2 different elements together. It's a bond. In order to break it, you have a chemical reaction. Intermolecular force is an attraction between 2 different molecules created by different things. Here it's because the molecules are polar. It's very weak compared to bonding. You do break these when you go from one state to the other. As you go from solid, liquid to gas, this is what gets impacted. So physical changes involve IMFs. Chemical changes involve covalent bonding, or the bonds themselves. So anytime you're talking about a chemical reaction, you are messing with the bonds. Anytime you have a physical change like melting, boiling, freezing, you're messing with the IMFs. And that's an important distinction to make. So they control the physical properties, vapor pressure, melting point, viscosities. So types of IMFs. There are 4 types. The strongest is ion dipole. This is top dog. London dispersion force is the weakest. Hydrogen bonding is the second strongest. Van der Waals forces, dipole-dipole is the third strongest. And then the last is going to be London dispersion forces. So that's your ranking, if you will. These are collectively called Van der Waals forces. And the answer for Van der Waals force is a fancy way of saying IMFs. Order of strength is as follows. Like I said, ion dipoles type, top, hydrogen bondings 2. And for those wondering, what the heck is an ion dipole? Here's what ion dipole is. You have Cl minus floating around. You have Na plus. So you're basically adding sodium chloride to water. What water does, it surrounds it, right? So water has a polarity, right? If you look at water, this is what water looks like. You have H, H. You have 2 lone pairs. This is going to have a negative dipole. This is going to have a positive dipole, positive dipole. What happens for ion dipole is that the positive end of water attracts the negative ions. So in this situation, you have O, H, H. So this is an ion dipole. The interaction between this chloride and that hydrogen. That's an ion dipole interaction. That's what it is. For sodium, it'd be the other end that interacts, right? Which is going to be the negative dipole end. That's an ion dipole. So ion dipole is nothing more, and it's typically water, by the way. I mean, you could have basically any polar molecule pull it off with an ion, but typically it's just going to be water. It's the interaction of the negative dipole with a positive ion and vice versa. That's very strong. That is stronger than hydrogen bonding, which involves any of the fun molecules. We'll talk about that in a second. Dipole-dipole is when you have polar molecules. Anytime you see a polar molecule, it's dipole-dipole. We talked about polarity, guys, right? Anytime it's a polar molecule, dipole-dipole. Don't analyze, don't think, just put it down. London dispersion, everything is London dispersion forces, so it's always there. Only question is it the strongest force? And we'll talk about that. The above is hierarchy, but is it possible? It is possible for London dispersion force to be stronger than hydrogen bonding, for example. So please do not, ingrain this in your head that hydrogen is always stronger and it can never be. If you have a big enough molecule with enough London dispersion forces, it can actually be stronger than hydrogen bonding. So please don't limit yourself into that line of thinking. They give you questions where the data makes it very clear the one with London dispersion forces is stronger, but students are so ingrained in their head that, oh, hydrogen bond's stronger, hydrogen bond. Don't do that. Always based on the data, and we'll talk about that in a little detail later. So first off, what the heck is the London dispersion force? It's because of electrons. So what happens temporarily, electrons will end up on the same side of an atom, just for a nanosecond, even less than a nanosecond. And because it does this, it creates a temporary dipole inside the atom. So it's going to be a negative end, it's going to be a positive end. And that temporary dipole will in turn get near another atom of helium and cause its two electrons to end up on the same end and create another dipole. It's called an induced dipole. So this is a temporary dipole. It gets near another helium atom, causes it to do the same thing where both electrons are on the same side. That's called an induced dipole, which now those two things can attract each other. Why? Because there's two different sides of attraction, right? The positive end attracts the negative end. These are very weak because they're temporary. They're not long term. And what impacts them is how many electrons you have. The more electrons you have, the more London dispersion force is. So atoms that are bigger in terms of size, that means number of electrons in shells, have more of them than the ones that have fewer ones. The atom with a temporary dipole then induces a dipole on the other, and now they can attract each other. That's what it basically is. Everything has this. Everything. How do you know which one's going to be stronger if just that's the only force involved? The ones that's bigger in size. I didn't say mass. I said size. You can use mass as a shortcut. Like what the relationship basically is, the bigger the mass of the molecules, usually the bigger the size, right? They're kind of connected. You use it as a shortcut, but you better never explain it in terms of mass. When you're doing explanations for this stuff, it better be in terms of size, because that's what really determines it. So strength impacted by size, with bigger atoms having more electrons, which allows more polarizability. That's the magical word you got to use. So if you're trying to explain London dispersion force, you would say, this is bigger in size and it's more polarizable, so it has stronger LDF. Voila. This is a fancy way of saying it has more electrons, so more potential for London dispersion force. The more electrons you have, the more polarizable it is, the more London dispersion force it could form. That's all that means. You just need to know to use it when you're explaining this stuff. Also impacted by shape with long skinny molecules having more LDF than compact molecules. So long and skinny looks like this, short and fat like this. So this will be like short and fat. I'm not going to draw everything around it. This is short and fat. Let's say we still have 4 to 5 carbons. This would be long and skinny. So when you have this has more LDF because it's got more surface area than this. So that's the other way you could tell. So you could tell by size or by shape. Shape is not as common, so don't lose sleep over it. But size is. All right. So here, these are all nonpolar molecules, right? Nonpolar molecules only have LDF. All these have LDF. So why the heck is it that the boiling point increases as you go down? Because guess what? The size increases. Now, you notice they use molecular weight here. Don't do that. You could shortcut it that way. But if you're explaining it, if I'm explaining this, I would say, oh, iodine has a larger size than fluorine and is thus more polarizable and has stronger LDFs. I would not say that iodine has a bigger mass than fluorine. Don't use the word mass. Size. Just remember size. Same thing here. You can see boiling point increases as you increase the size because once again it's more polarizable. So that's how you explain. If they only have LDF, and all these do because they're single elements or they're nonpolar, then the bigger the size, the bigger the LDF. All right, dipole. Anytime it's polar, it's dipole. We talked about polarity, how if you have a lone pair off the middle, it's polar. You're just going to roll with that. Anytime you see a polar molecule, it's dipole. Hydrogen bonding is a little trickier. Interaction between two compounds containing hydrogens bond to F or N. You see how these hydrogens are coming off the N? That's hydrogen bonding. You see how these hydrogens are coming off the O? Hydrogen bonding. This would not be hydrogen bonding. This is carbon. This is not an example of hydrogen bonding because it's not F or N. The central atom has to be F or N. You could have hydrogen bonding. You see how it's between ammonia and H2O, two different molecules. Why is it possible? Because these are both, the central atoms are both either F or N. I cannot do hydrogen bonding with this. You cannot do this. Like have NH3 again. Do the same thing as you did above. Connect. This is not hydrogen bonding. Why? this is not F or N. Both of the molecules have to have F or N. I can't emphasize this enough. So remember that. Both of them have to be F or N in order for it to be hydrogen bonding. And hydrogen bonding, by definition, by the way, and they're going to ask you a question on this because they always ask students to draw hydrogen bonding. It's between the hydrogen of one molecule that has F or N as a central atom with another molecule's lone pair. That's what hydrogen bonding is. The way you represent it, either with these three dots or with a slash, slash, slash. That is hydrogen bonding. It's between the H of one molecule and the lone pair of another. It is not between two H's. It's not between H and some random spot. It's between the lone pair and the H. Please remember that. You're guaranteed a question on this. And once again, remember both molecules. So when you're doing comparison, make sure both of the central atoms in the two molecules involved have F, O, or N. Otherwise, it's not hydrogen bonding. Ion dipoles between an ion and a molecule. And we talked about that a little earlier. So here's an example of an ion dipole. This is a positive ion. Here's a negative ion. Once again, you can see the end of the water molecule that's attracted. All right, so let's try some. Determine the type of intermolecular force expected for each. C6H6. I don't need to even look at this. There's only C and H. This is nonpolar. So guess what? This is just going to be LDF. Done deal. That's all you got to do. Don't think. This has CH3OH. So if you draw the Lewis structure, this would have an O here. H, 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 and there. Okay. It's not symmetrical. How do I know that? You see how this CNO has a dipole and the CNH has a dipole, but they don't cancel each other's out. So this is going to be polar. And if it's polar, it's got dipole-dipole automatically, right? London's automatically for everything. And because there's an OH here, there's your hydrogen bonding. So that's all three forces. So which one of these would have a higher boiling point? C6H6 or CH3OH, CH3OH. Why? Because hydrogen bonding is stronger than LDF. The stronger the force, the higher the boiling point. Next one, CH3 and H2. What does it have? I'm going to draw a skeleton. H, H, lone pair, H, H, H. So right off the bat, you know it's polar, right? Because it's something besides just C and H. So that's polar. So dipole is guaranteed. You have N and H. That's a hydrogen bond, right? So that's definitely there. And LDF is automatic, so that's all three again. CF4 would look like this. Symmetrical, all the F's cancel out, so it's going to be LDF. There's no dipole, there's no hydrogen bonding. SO3 we've done before. It's a resonance structure, and resonance structures without a lone pair are always nonpolar. Nonpolar is always LDF. And the last one looks like this. You have O in the middle. This is one of those situations where you have something besides C as the middle, which is strange. But on the AP exam, they give you what's called the structural formula to tell you how the bonding is occurring. If I told you this was C2H6O, you would have no idea it looks like this. But what they'll do kindly for you guys, they'll show you exactly how the bonding occurs. So it's carbon with 3 hydrogens connected to an O, connected to a carbon with 3 H. So they're actually telling you exactly how the Lewis structure goes. It's a nice little feature for them. This is Coke, by the way, so hopefully you understand this is also an ether, right? If you're going to make it a functional group question. All right, and as far as the polarity, remember, if it's C and H only, it's nonpolar. Anything else become polar, so it's going to have dipole guaranteed. LDF is guaranteed. Does it have hydrogen bonding? No, because you see how the O doesn't have the H. Just because there's an H somewhere there doesn't matter. The H has to be off the F or N. So it's going to be dipole in London. All right, evaporation, the escape of molecules from the surface of a liquid to a gas phase, doesn't require boiling. This just occurs because the molecules at the surface of any liquid has the most energy. And over time, they're going to get energy from either the molecule or the surroundings, and they're going to become a gas. Evaporation occurs when you put a cup of water on your table, and over time, you'll see the water go away. That's just evaporation. Doesn't mean you made it go to 100 degrees to do it. Liquids with strong IMFs evaporate slower. Why is that? the stronger the IMF, the more energy you have to put in order to weaken that IMF, actually break it. Because when you're going from liquid to gas, you break IMFs and become a gas. So in this situation, the stronger the IMF, the less likely it's going to become a gas because you put a lot of energy to make it happen. So that's why water evaporates much more slowly than a substance like, let's say, gasoline. So for our purposes, strong IMFs is equal to low evaporation is equal to high boiling point. And where did the boiling point come in? Well, common sense, right? If you have strong IMFs, you have to put more energy in to break those bonds again. So when you're boiling something at 100 degrees, you have to put more energy in to break. So the stronger the IMF is, the more energy you have to put in, the higher the boiling point. Boiling point is basically what happens, the temperature you need to put in, or the energy you need to put in order to make the atmospheric pressure equal the vapor pressure. So what does this all mean in English? So here's what happens. Let's say you have a bowl of water, or pot of water, I should say. So here's your water. From the surroundings, you have what's called atmospheric pressure. So there's air all around us, right? That air is attracted to the ground by gravity. The exact pressure we all experience is about 1 atmosphere. That's about surface, for the most part. Ours is probably a little lower because we're in higher elevation. But at sea level, you experience exactly 1 atmosphere of pressure. That's basically due to all the gas around you being pushed onto you because of gravity. That's 1 atmosphere. When a liquid becomes a gas, it creates vapor pressure. Why? Because now these gas molecules collide with the surface and they create pressure. That's what vapor pressure is. The pressure of the liquid is called vapor pressure. When this pressure equals the atmospheric pressure, you boil. That's all boiling is. When the vapor pressure equals atmospheric pressure, we have boiling. You see bubbles. That's why if you go in higher elevation where the pressure is lower, your water boils at a lower temperature. So typically we need 100 degrees Celsius to make that happen for water, right? But what if you have really strong IMFs? What if it's not water? What if it's something else? Then the boiling point's going to go up. So that's what this whole relationship comes from as far as strong IMFs means low evaporation, which means high boiling point. It also means, technically, low vapor pressure. That's the loop you have to memorize. Is that when you have strong IMFs, you're going to have low evaporation, you're going to have high boiling point, and you're going to have low vapor pressure. Why low vapor pressure, you're wondering? If you have strong IMFs, are you going to make a lot of the liquid become a gas? No, very little is. So that's why the vapor pressure is going to be low. So vapor pressure is the pressure develops in the gas phase above a liquid when it's placed in a closed container due to evaporation or boiling, whatever you like. Boiling occurs when the vapor pressure of the liquid equals atmospheric pressure. So here is the boiling point of different substances. You can see for diethyl ether, it's about 30 degrees Celsius. For alcohol, it's about 78. For water, it's 78, or 100, excuse me. And ethylene glycol, which is antifreeze, it's a lot higher. So that's what boiling point basically is. When atmospheric pressure equals vapor pressure. And you can see it varies based on the IMF. So which one of these has the strongest IMF? Ethylene glycol. Why? Because this boiling point is way higher. Like you can't even see it based on this graph. Relationship of vapor pressure with boiling point. We already talked about the stronger the IMF, the lower vapor pressure, and the higher the boiling point. The other thing I want to go over is capillary action. Explains why fluids are often drawn up into other substances. So how the heck does a tree that's 50 meters tall able to get water from its roots all the way up there to its leaves? It's because of capillary actions. Capillary action is basically due to the fact that there's 2 forces involved. We can use water as an example because it's the easiest one. Water has 2 forces. It has cohesive forces, which are the forces between water molecules. So cohesive, their attraction to each other. And it has the adhesive force, which is the attraction to something else. So in the case of something else here, it's going to be to the roots of the plant. When cohesive forces are greater, water does not go up. But when adhesive attractions are bigger, you have what's called capillary action. So the way capillary action basically works, the less surface area that you're touching with the water molecule, the greater adhesive forces are going to be, and the higher the water goes. So you can imagine the roots having very, very small widths inside of them. Like, even though it's a gigantic root, each one of the ones that actually cause the water to travel up it is a very small. So when water tries to travel, it's traveling through a very small surface area substance, and that's why it goes higher. You can see that the smaller the surface area, you can see how there's very little contact, the less the water rises. So if you want water to rise higher, you need to have a narrower tube. So capillary action is when adhesion to the walls is stronger than cohesive forces between the liquid molecules, which allows the liquid to move up. Examples are water climbing the roots of a plant, which is the most common. So if we should find determine which is a lower boiling point. All right, so these are both nonpolar, right? It's got 14 hydrogen versus 18. So which is bigger in size? This is. The bigger in size means stronger LDFs. So LDFs are stronger, which means lower boiling point. So C6H14 is a lower boiling point, or C6H18 is a higher boiling point, same thing. For this one, C6H14, you know this is nonpolar, right? So LDF only. Here, LDF, but you see how they attach O to H for you? Remember, it's a structural formula. This is hydrogen bonding. This is also going to have dipole-dipole, right? That's a lot of forces. All those are stronger than the LDF of C6H14. So C6H14 is going to have a lower boiling point because C6H13 has stronger force, is going to have a higher boiling point. For this one, look identical, right? The only difference is Cl and F. But F is a fun molecule. This is hydrogen bonding. This is not. So HCl is going to have a lower boiling point. All right, the last thing, phase diagrams. So phase diagrams involve the following. These are the different terms you need to know. You know, vaporization, going liquid to gas. Gas to liquid is condensation. Solid to gas is sublimation. This is a weird word that you want to memorize. Gas to solid, on the other hand, is deposition. All the other ones kind of make sense, except sublimation and deposition, to be honest with you. I think you already know all the other ones. Freezing is when you go from liquid to solid, and when you're going from solid to liquid, you are melting. So those are the ones you need to know. All right, here is a heating curve. The things you need to know about a heating curve is basically the following. First off, these diagonal lines are single states, so this is just a solid, this is just a liquid, this is just a gas. Your horizontal line is when you have two states existing simultaneously. Here, you have solid plus liquid. What's happening is that as you put energy in, you're trying to melt all the solid, right? Until all the solid melts at exactly this point, you have solid and liquid together. Once you get to this point and all the solid's gone, then what happens? The temperature spikes. The reason is that all the energy you're putting in at this point is it's being used to make the solid turn to liquid. Once all the solid's gone, now the temperatures start going up, the molecules can start moving faster, and you get liquid. So your kinetic energy increases at the vertical line. So your KE goes up here, and goes up here. What about the horizontal line? KE is 0, because your temperature changes 0. Your KE is not changing. Then you go liquid, and then you liquid, water, and vapor. So here at this point, you have liquid and gas. And then right here, all the liquid is gone, and you have pure gas, so the temperature spikes again. So steam is actually higher temperature and more dangerous for you than boiling water, in case you didn't know. So temperature and kinetic energy constant in horizontal lines, what we just stated. Temperature changes only at diagonal lines where single state exists. So remember that temperature only exists at the diagonals. You can tell that based on the graph. By the way, which one of these requires more energy to make something melt, or make this thing melt, or to boil? The answer is boil. That's because the line is longer. So when you're comparing random things together, if the line is longer for this than this, which usually is, it means you need more energy. All right, the other thing we're going to go over is phase diagrams, and this is the last thing. So we talked about heating curve, which is one example of a phase diagram technically. This is what's referred to, I should call this a heating curve, and this a phase diagram to make the distinction. So let me do that now. So phase diagrams involves all three states. It relates pressure versus temperature. So it relates the temperature and pressure of a single substance. So the things you need to be able to read from this You need to know the triple point, which is when all three states exist simultaneously. So here, solid, liquid, and gas, all three of them are there at the same time. You need to understand that your melting temperature depends on the pressure. So anything along the melting is along this line. So at this pressure, this is the melting point. At this pressure, it's this. At this, it's this. So as you increase the pressure, you can see that the melting point changes. So that's one thing to be aware of. So the melting point is based on wherever the temperature and pressure line intersect. So anything along these lines, anything along this line, all the way here is called your melting point. The normal melting point is going to be point D for this substance because it's going to be 1 atmosphere. That's the normal melting point. But if you need to melt it at any lower pressure, then you would need to have a different temperature, obviously. The other thing to note is that the liquid and gas line, anything along that, same thing as the melting point, anything along here is called the boiling point. What's the normal boiling point? Wherever it is at 1 atmosphere, because that's the normal boiling point. But you can see it varies. Same thing with sublimation, deposition. So what do you use this for? Basically, what they're going to do is tell you that you have a substance at, let's say, 0.5 atmospheres, and your temperature is increasing. What happens to the substance? Well, based on this phase diagram, at 0.5, as you increase temperature, your substance goes from a solid to a liquid, which means it is doing what? It's melting. And then as you continue on, it's going from a liquid to a gas, which means it's going to be vaporizing. That's the kind of stuff you need to be able to tell, and also what these different lines represent. Critical point, by the way, at this temperature, liquid doesn't really exist. That's the significance of it. And the triple point, like I said, is when all three states. Anywhere on line AB represents the boiling point. Anywhere on line AD represents the melting point. Anywhere on AC represents the sublimation point, the ones we talked about a second ago. You could also tell the density. The least dense is always going to be gas, at least for our purposes. There are situations where that's not true, but we don't care about those. The way you tell is you're going to draw a vertical line between the solid and liquid. Sorry, went a little too fast. So draw a vertical line, and this is going to be a horrible line, so I want to apologize. And then you see which way the line between the liquid and the solid is pointing. This is the liquid to solid line, right? You see how it's pointing more toward the solid than it is the liquid? That means that here the solid is less dense. Now, compare that to this, where we have, say that's your vertical line. See how here it's pointing more toward, this is solid. The solid is going to be solid, liquid, and gas. You see how this line here is pointing more toward the liquid? That's going to mean the liquid is less dense. So you could tell the density based on which way the line between the solid and the liquid points. If it points to the left, the solid is less dense. If it points to the right, the liquid is less dense. Reality is that the only time that the solid is less dense is ice. Usually solid is more dense, right? Common sense. Ice is the exception because when hydrogen bonding occurs, it creates space between the water molecules, and that's what makes it less dense. That's the scientific reason. For our purposes, it's the only time it really happens. Every other time, you're going to see it more like this. But I just want you to understand how to determine what's less dense and what's more. You can see here H2O versus CO2C. This is more obvious, right? See how this points toward the liquid. See how this one points toward the solid. So that's what you can use to determine it. So that's bonding and IMFs in a nutshell.